465 miles per hour. In 1944, that number seemed impossible. Fighter aircraft were pushing against an invisible wall, a barrier of physics and engineering that no amount of horsepower seemed capable of breaking through. The fastest planes in the world were struggling to exceed 400 miles per hour in level flight, and every engineer from London to Los Angeles believed they understood why. The propeller, that spinning disk of wood and metal that had carried mankind through the skies since the Wright brothers, was reaching its physical limits. At high speeds, the tips of propeller blades approached the speed of sound, creating shockwaves that robbed engines of their power and aircraft of their speed. But in a cluttered office at the Supermarine Aviation Works in Southampton, a 53-year-old engineer named Joseph Smith was about to prove them all wrong. Not with a revolutionary new engine, not with some theoretical breakthrough that existed only on paper. He was going to take Britain's most beloved fighter, the legendary Spitfire, and transform it into something the world had never seen before. His solution was so unconventional, so seemingly backward, that his colleagues initially laughed. Two propellers, spinning in opposite directions, on the same engine shaft. They called it ridiculous. They called it unnecessarily complicated. They said it would never work. They were wrong. Before we dive into this incredible story of engineering genius and wartime innovation, if you're fascinated by the untold stories of aviation history, make sure to hit that subscribe button and give this video a thumbs up. Your support helps us bring more of these remarkable stories to light. To understand why Joseph Smith's twin propeller design was so revolutionary, we need to go back to the beginning. We need to understand the Spitfire itself and the man whose vision created it. Reginald Joseph Mitchell was born in 1895 in Stoke-on-Trent, England, a city famous for its pottery factories and working-class families. His father was a schoolteacher, and young Reginald showed an early aptitude for mechanical things. He would spend hours in his father's workshop, taking apart clocks and reassembling them, sketching designs for machines that existed only in his imagination. At 16, Mitchell left school and became an apprentice at a locomotive engineering firm. It was there that he first learned the fundamentals of design and manufacturing, the practical skills that would later make him one of the most influential aircraft designers in history. But locomotives were earthbound, and Mitchell's dreams were in the sky. In 1917, at the age of 22, Mitchell joined the Supermarine Aviation Works in Southampton. The company specialized in flying boats and seaplanes, and Mitchell rose quickly through the ranks. By 1920, he was chief designer. He was only 25 years old. Throughout the 1920s, Mitchell designed a series of racing seaplanes for the prestigious Schneider Trophy competition. These sleek, powerful aircraft pushed the boundaries of aviation technology, winning the trophy for Britain in 1927, 1929, and 1931. The last of these, the Supermarine S.6B, set a world speed record of 407 miles per hour, a staggering achievement for its time. But Mitchell was not content with building racing planes. He could see the storm clouds gathering over Europe, could sense that another great war was coming. And he knew that Britain would need fighters, fast and maneuverable aircraft that could defend the island nation from aerial attack. In 1934, Mitchell began work on a new design. The Air Ministry had issued Specification F-730, calling for a new fighter to replace the aging biplanes that equipped the Royal Air Force. Mitchell's first attempt, the Type 224, was a disappointment. It was too slow, too ungainly, too conventional. Mitchell himself called it a failure. But failure was not in Mitchell's nature. He went back to his drawing board and started over. This time, he threw away the rulebook. He incorporated everything he had learned from his racing seaplanes, the streamlined fuselage, the thin elliptical wings, the retractable landing gear. He designed an aircraft that was beautiful and deadly, a machine that seemed to belong to the future rather than the present. The new design flew for the first time on March 5, 1936. The test pilot, Captain Joseph "Mutt" Summers, climbed out of the cockpit after the flight and reportedly said just 4 words: "Don't touch anything." The aircraft was perfect. They called it the Spitfire. But Mitchell would not live to see his creation in its finest hour. In 1937, at the age of 42, Reginald Mitchell died of cancer. He had known he was dying for years, had pushed himself relentlessly to complete the Spitfire before his time ran out. He succeeded, but just barely. The job of developing and improving the Spitfire would fall to others. Chief among these was Joseph Smith. Smith had worked alongside Mitchell at Supermarine since 1921, and he understood the Spitfire better than anyone alive. When Mitchell died, Smith became chief designer, and he devoted the next decade of his life to making the Spitfire faster, more powerful, and more deadly. The challenge facing Smith was immense. When the Spitfire first entered service in 1938, it was powered by a Rolls-Royce Merlin engine, producing just over 1,000 horsepower. This was impressive for its time, but Smith knew it would not be enough. German aircraft were improving rapidly, and the Luftwaffe would soon field fighters that could match or exceed the Spitfire's performance. Throughout the early years of the war, Smith and his team worked continuously to upgrade the Spitfire. They fitted more powerful engines, redesigned the wings, improved the armament. Each new mark of Spitfire was faster and more capable than the last. But by 1943, they were running into a fundamental problem. The Rolls-Royce Griffon engine, which had replaced the Merlin in the latest Spitfires, was producing over 2,000 horsepower. This was an enormous amount of power, enough to propel the aircraft to speeds that would have seemed impossible just a few years earlier. But there was a catch: the propeller. A propeller works by converting the rotational energy of an engine into thrust. The blades spin through the air, pushing it backward and propelling the aircraft forward. In principle, it is simple. In practice, it is extraordinarily complex. As an aircraft flies faster, the propeller must spin faster to produce the same amount of thrust. But there is a limit to how fast a propeller can spin. As the tips of the blades approach the speed of sound, strange things begin to happen. Shock waves form on the blade surfaces. Drag increases dramatically. The propeller becomes less efficient, wasting more and more of the engine's power. This is known as compressibility, and it was the great enemy of aircraft designers in the 1940s. Every major aviation power was struggling with the same problem. The engines were producing more power than ever before, but the propellers could not convert that power into speed. The obvious solution was to make the propeller larger, to spread the power over a greater blade area. But this created new problems. A larger propeller required longer landing gear, which added weight and complexity. It also increased the torque reaction, the tendency of the aircraft to roll in the opposite direction of the propeller's rotation. Torque reaction was already a serious issue with the Griffon-powered Spitfires. The engine was so powerful that it could literally twist the aircraft off the runway if the pilot was not careful. Many inexperienced pilots had crashed during takeoff, unable to control the violent yawing motion caused by the engine's enormous torque. Joseph Smith had been wrestling with these problems for months. He had tried different propeller designs, different blade angles, different materials. Nothing seemed to work. The Griffon engine was capable of producing nearly 2,500 horsepower, but the propeller could only harness a fraction of that potential. And then, in the summer of 1943, he had an idea. What if, instead of one large propeller, he used 2 smaller propellers? What if those propellers rotated in opposite directions, one clockwise and one counterclockwise? The torque from one propeller would cancel out the torque from the other. And because the blades were smaller, They could spin faster without reaching the speed of sound. It was not an entirely new idea. Contra-rotating propellers, as they were called, had been experimented with before. The concept dated back to the 19th century, and several aircraft had flown with such systems, but they had always been plagued by problems. The mechanical complexity was enormous. 2 propellers meant 2 gearboxes, 2 sets of pitch controls, 2 of everything. The weight penalty was significant, and the maintenance requirements were nightmarish. Smith did not care. He was convinced that contra-rotating propellers were the key to unlocking the Spitfire's full potential, and he was determined to make it work. The first challenge was the gearbox. A conventional propeller is connected directly to the engine crankshaft through a reduction gear. The reduction gear slows down the propeller rotation, allowing the engine to run at its optimal speed, while the propeller turns at a more efficient rate. For contra-rotating propellers, Smith needed a gearbox that could take the power from a single engine and split it between 2 propeller shafts rotating in opposite directions. This required a complex arrangement of gears, bearings, and seals, all operating under enormous stress and at extremely high temperatures. Smith turned to Rotol, a joint venture between Rolls-Royce and Bristol that specialized in propeller design. The engineers at Rotol were skeptical. They had seen contra-rotating systems fail before. But Smith was persuasive. And more importantly, he had the backing of the Air Ministry. The war was entering a critical phase, and any technology that could give British fighters an edge was worth pursuing. Working around the clock, the Rotol team designed a new gearbox specifically for the Spitfire application. It used a planetary gear system, with a central sun gear driving 2 ring gears that rotated in opposite directions. Each ring gear was connected to one of the 2 propeller shafts. The engineering challenges were immense. The gears had to be manufactured to incredibly tight tolerances, with surface finishes measured in millionths of an inch. The bearings had to withstand forces that would have destroyed conventional components. The oil system had to keep everything lubricated and cool, even under the most extreme conditions. But piece by piece, component by component, the system came together. By early 1944, the first contra-rotating propeller unit was ready for testing. The test aircraft was a Spitfire Mark 15, serial number NN660. It was fitted with a Griffon 61 engine, producing 2,050 horsepower, and the new Rotol contra-rotating propeller unit with 6 blades, 3 on each hub. The first flight took place on January 27, 1944. The test pilot was Geoffrey Quill, one of the most experienced Spitfire pilots in the world. Quill had been with the program since the very beginning, had flown the prototype alongside Mutt Summers back in 1936. If anyone could evaluate the new system, it was him. Quill later described that first flight in his memoirs. He wrote that the difference was immediately apparent. The violent torque swing that plagued conventional Griffon Spitfires was almost completely eliminated. The aircraft tracked straight down the runway, requiring only minimal rudder input to maintain direction. It was, he said, like flying a completely different airplane. But the real surprise came when Quill opened the throttle in level flight. The Spitfire accelerated with a ferocity he had never experienced before. The airspeed indicator climbed steadily, passing 400 miles per hour, then 420, then 440. Finally, at just under 460 miles per hour, the aircraft reached its limit. Quill was astounded. No Spitfire had ever gone this fast. No propeller-driven aircraft in British service had ever gone this fast. The contra-rotating propeller had worked exactly as Smith had predicted, converting the Griffon's massive power into pure speed. But speed was only part of the equation. A fighter aircraft must be able to climb, to turn, to maneuver in combat. Over the following weeks, Quill and other test pilots put the modified Spitfire through its paces, evaluating every aspect of its performance. The results were extraordinary. The rate of climb was improved by nearly 15% compared to conventional Griffon Spitfires. The service ceiling was increased by several thousand feet, and most importantly, the handling characteristics were dramatically improved. The absence of torque made the aircraft more stable and predictable, easier to fly and easier to fight. There was, however, a price to pay. The contra-rotating propeller unit added nearly 300 pounds to the aircraft's weight. The mechanical complexity meant more things could go wrong, more parts that could fail, and the maintenance requirements were significant, with the gearbox needing careful attention after every few hours of flight. Smith and his team worked to address these issues. They refined the gearbox design, reducing weight and improving reliability. They developed new maintenance procedures that minimized downtime. They trained ground crews to service the complex systems efficiently and effectively. By the summer of 1944, the contra-rotating Spitfire was ready for production. The Air Ministry designated it the Spitfire Mark XIV with contraprops, though informally it became known simply as the CR Spitfire. Initial orders called for 500 aircraft, with deliveries to begin in early 1945. But even as the production lines were being set up, Smith was already thinking ahead. The Mark XIV with contraprops was impressive, but he knew it was not the ultimate expression of the Spitfire concept. The Griffon engine still had more potential to be unlocked. In 1944, Rolls-Royce was developing a new version of the Griffon engine. Designated the Griffon 85, it incorporated a two-stage, two-speed supercharger and other improvements that boosted output to over 2,400 horsepower. This was an enormous amount of power, more than double what the original Spitfire had possessed. Smith immediately saw the possibilities. Combined with the contra-rotating propeller, the Griffon 85 could produce a Spitfire capable of speeds approaching 500 miles per hour. It would be the fastest propeller-driven aircraft ever built, a machine that could outrun any fighter in the world. Work began on the new variant in late 1944. Designated the Spitfire Mark 68, in its initial form, it featured a strengthened airframe, increased fuel capacity, and the new Griffon 85 engine with contra-rotating propeller. The modifications were extensive, touching virtually every system on the aircraft. The first prototype flew in February 1945. Once again, Geoffrey Quill was at the controls. And once again, the results exceeded all expectations. In level flight at optimal altitude, the new Spitfire reached 465 miles per hour. This was an astonishing achievement, a speed that would have seemed like fantasy just a few years earlier. The Spitfire had evolved from a fighter capable of 360 miles per hour to one that could outrun virtually any aircraft in existence. The climb rate was equally impressive. The new Spitfire could reach 20,000 feet in less than 7 minutes, a performance that outclassed every operational fighter in the world. At high altitude, where the air was thin and most engines struggled, the two-stage supercharger kept the Griffon breathing freely, maintaining power output that would have been impossible with conventional designs. But the war was ending. By the time the first production contra-rotating Spitfires rolled off the assembly line, Germany had surrendered. Japan would follow a few months later, brought to its knees by atomic fire and Soviet invasion. The great conflict that had driven aviation technology to such heights was over. The timing was bittersweet for Joseph Smith. He had devoted years of his life to perfecting the Spitfire, had pushed the boundaries of what was possible with propeller-driven aircraft. And now, just as his greatest achievement was reaching fruition, the need for it had evaporated. The contra-rotating Spitfires that did enter service proved to be magnificent machines. They equipped several Royal Air Force squadrons in the immediate post-war period, serving with distinction until they were gradually replaced by jet fighters in the late 1940s. Pilots who flew them spoke of their speed, their climb rate, their beautiful handling characteristics. But the era of the propeller fighter was ending. The jet age had dawned, and the Spitfire, no matter how refined, could not compete with the new technology. The Gloucester Meteor and de Havilland Vampire were already in service, and faster, more capable jets were under development. The contra-rotating Spitfire was the pinnacle of a technology that had become obsolete. Joseph Smith accepted this reality with characteristic grace. After the war, he remained at Supermarine, working on new projects including the experimental Attacker jet fighter. He never forgot the Spitfire, though. It remained his proudest achievement, the aircraft to which he had devoted the best years of his professional life. In reflecting on the contra-rotating propeller development, Smith later wrote that it represented a vindication of engineering principles. The solution to the Spitfire's speed limitations had not required revolutionary new technology or theoretical breakthroughs. It had required a willingness to question assumptions, to look at old problems from new angles, to persist in the face of skepticism and doubt. The twin propeller design that his colleagues had called ridiculous had proven to be anything but. It had extracted the maximum possible performance from the piston engine and propeller combination, pushing against the very limits of physics. And in doing so, it had created what many consider to be the finest propeller-driven fighter ever built. The story of the contra-rotating Spitfire is, in many ways, a story about the nature of innovation itself. Great breakthroughs do not always come from exotic new technologies or radical departures from the norm. Sometimes they come from a deeper understanding of existing systems, from the patient work of engineers who refuse to accept that a problem cannot be solved. Joseph Smith was such an engineer. He understood the Spitfire better than anyone, understood its strengths and its limitations, its potential and its constraints. When he encountered a barrier that seemed insurmountable, he did not give up. He went back to first principles, thought about the problem from every angle, and found a solution that others had dismissed as impractical. The contra-rotating propeller was not a new idea, but in Smith's hands, applied to the Spitfire with careful attention to every detail, it became something transformative. It turned a great fighter into an extraordinary one, a machine that could fly faster than any propeller-driven aircraft had flown before. There is something poignant about the timing of this achievement. The contra-rotating Spitfire reached its peak performance just as the technology it represented was becoming obsolete. It was a final flourishing, a last demonstration of what was possible before the old order gave way to the new. But perhaps that makes the achievement even more impressive. Smith and his team were not working towards some distant future goal. They were solving immediate problems, meeting urgent needs, pushing the boundaries of the possible in real time. They did not have the luxury of waiting for better technology to come along. They had to make the best of what they had. And what they made was remarkable, 465 miles per hour. In 1944, that was a speed that belonged to the realm of dreams. Joseph Smith and the contra-rotating Spitfire made it reality. The legacy of this achievement extends beyond the aircraft itself. The engineering principles that Smith applied, the contra-rotating propeller concept, the careful attention to weight and balance, the innovative gearbox design, all of these influenced subsequent aviation development. When turboprop engines became practical in the 1950s and 60s, many of them used contra-rotating propellers based on the same principles that Smith had pioneered. The Rolls-Royce engineers who developed the gearbox for the Spitfire went on to design similar systems for commercial aircraft. contributing to the development of the Avon and Tyne turboprops that powered many post-war transport planes. The lessons learned from the Spitfire program spread throughout the aviation industry, influencing designs for decades to come. But perhaps the most important legacy is the story itself. In an age of increasingly complex technology, when problems often seem too big and too difficult for individual human beings to solve, the story of the contra-rotating Spitfire offers hope. It reminds us that engineering is fundamentally a human endeavor, that great achievements come from human minds, working with patience, creativity, and determination. Joseph Smith was not a superhuman genius. He was a skilled engineer who understood his subject deeply and refused to accept that a problem could not be solved. When he looked at the Spitfire and saw that it could go faster, he found a way to make it happen. When others told him his idea was ridiculous, he proved them wrong. That kind of persistence, that refusal to accept limitations, is what drives human progress. It is what took us from wooden biplanes to supersonic jets in the span of a few decades. It is what continues to push the boundaries of what is possible in aviation and in every other field of human endeavor. The contra-rotating Spitfire was not the last word in fighter design. It was surpassed by jets within a few years of its introduction. But it remains a testament to what can be achieved when engineering skill is combined with determination and vision. It remains a reminder that sometimes the most radical solutions come from the most careful thinking. 465 miles per hour. A ridiculous twin-prop design, a beast of an aircraft that could outfly anything else in the sky. That was Joseph Smith's gift to aviation history. That was the final, magnificent evolution of Reginald Mitchell's legendary Spitfire. And it all started because one engineer refused to believe that a problem could not be solved. The story of the Spitfire's development during World War II is, in many ways, a microcosm of the entire conflict. It was a war of production, of innovation, of constant improvement. The nations that could develop and deploy new technologies fastest were the nations that would ultimately prevail. Britain understood this from the very beginning. When the war began in September 1939, the Royal Air Force was equipped with Spitfires powered by Merlin engines, producing just over 1,000 horsepower. By the war's end, the latest Spitfires had engines producing nearly 2.5 times that power and speeds to match. This progression was not automatic. It required constant effort, constant innovation, constant willingness to try new approaches. The contra-rotating propeller was just one of dozens of innovations that kept the Spitfire at the cutting edge throughout the war. Each improvement built on the ones before, each solution created new problems that demanded new solutions. The men and women who made this possible rarely received the recognition they deserved. Joseph Smith's name is not as famous as Reginald Mitchell's, even though Smith was responsible for developing the Spitfire through most of its operational life. The engineers at Rotol who designed the gearbox are almost entirely forgotten. The test pilots who risked their lives proving new systems are remembered only by aviation historians, but their achievements speak for themselves. The Spitfire that fought in the Battle of Britain in 1940 was a good aircraft. The Spitfire that emerged from the war in 1945 was an exceptional one. That transformation was the result of thousands of individual decisions, thousands of small improvements, thousands of problems solved by dedicated engineers working under enormous pressure. The contra-rotating propeller represents the culmination of this process. It was the final answer to a problem that had plagued aircraft designers for years. It was an elegant solution, converting the limitations of existing technology into an advantage. And it produced an aircraft that could fly faster than any propeller-driven fighter before or since. There is something deeply satisfying about this kind of engineering achievement. It is not flashy or glamorous. It does not involve dramatic breakthroughs or sudden revelations. It is the product of patient, methodical work, of understanding problems deeply and solving them systematically. Joseph Smith embodied this approach. Throughout his career, he was known for his thoroughness, his attention to detail, his willingness to revisit and refine his designs until they were as good as they could possibly be. He was not interested in fame or recognition. He was interested in making aircraft that worked, that performed their mission safely and effectively. The Spitfire was the canvas on which Smith painted his masterpiece. He took an already excellent design and made it better, then better again, then better still. Each mark of Spitfire was an improvement on the one before, a step forward in the endless pursuit of perfection. The contra-rotating propeller was his final brushstroke. It was the innovation that allowed the Spitfire to reach its full potential, to achieve speeds that would have seemed impossible when the aircraft first flew in 1936. It was the capstone of a career devoted to making one of history's greatest aircraft even greater. The technical details of the contra-rotating propeller system are fascinating in themselves. The gearbox that Rotol developed was a marvel of precision engineering. It had to transmit enormous power, over 2,000 horsepower, through gears and bearings that operated at extremely high speeds. The tolerances involved were measured in 10,000ths of an inch. The slightest imperfection could cause catastrophic failure. The propeller blades themselves were carefully designed to operate efficiently at the higher rotational speeds that the contra-rotating system allowed. Each blade was a sophisticated airfoil, shaped to produce maximum thrust while minimizing drag and noise. The pitch control system could adjust the angle of all 6 blades simultaneously, optimizing performance for takeoff, climb, cruise, and combat. The integration of all these components into the Spitfire airframe required careful attention to balance and weight distribution. The contra-rotating propeller unit was heavier than a conventional propeller, and this weight was concentrated at the nose of the aircraft. Smith and his team had to redesign the fuselage structure to handle the additional loads, strengthen the engine mounts, and adjust the fuel and ammunition distribution to maintain proper center of gravity. These were not glamorous tasks. They did not make headlines or inspire movies, but they were absolutely essential. Without this careful, methodical engineering work, the contra-rotating Spitfire would never have flown. The brilliant concept would have remained just that, a concept never realized in metal and flight. This is the reality of engineering. The big ideas get the attention, but the success of those ideas depends on countless small decisions made correctly. Joseph Smith understood this better than most. He knew that the difference between a good aircraft and a great one often came down to details that most people would never notice. The pilots who flew the contra-rotating Spitfires certainly noticed. They spoke of how the aircraft tracked straight down the runway, without the violent torque swing that made conventional Griffon Spitfires so challenging to fly. They marveled at the acceleration, at the way the aircraft seemed to leap forward when the throttle was opened. They appreciated the improved handling at high altitude, where the reduced torque made the aircraft more predictable and easier to control. These improvements translated directly into combat effectiveness. A pilot who did not have to fight his aircraft on every takeoff could focus his attention on the mission ahead. An aircraft that could accelerate quickly could escape from a disadvantaged position or close rapidly with a fleeing enemy. Better high-altitude handling meant better performance, where many air battles were fought. The contra-rotating Spitfire never had the opportunity to prove itself in large-scale combat. By the time it entered service, the war was ending. But the pilots who flew it were unanimous in their assessment. It was the finest propeller-driven fighter ever built. That assessment has stood the test of time. In the decades since the war, aviation historians have studied the contra-rotating Spitfire extensively. They have compared its performance to other late-war fighters, to the North American P-51H Mustang, the Republic P-47N Thunderbolt, the Hawker Tempest. And consistently they have reached the same conclusion. The contra-rotating Spitfire was faster, climbed better, and handled more precisely than any of its contemporaries. This is Joseph Smith's legacy. This is what he achieved with his ridiculous twin-prop design. He created an aircraft that was the best of its kind, the pinnacle of propeller-driven fighter development. He pushed the boundaries of what was possible and proved that there was still room for innovation, even in a technology that seemed to have reached its limits. The story of the contra-rotating Spitfire is also a reminder of how quickly technology evolves in wartime. At the start of World War II, fighters were mostly fabric-covered biplanes with fixed landing gear and open cockpits. By the end, they were sleek metal monoplanes capable of speeds approaching 500 miles per hour. This transformation happened in just 6 years, driven by the terrible urgency of war. The Spitfire embodied this transformation more than any other aircraft. It began the war as a state-of-the-art fighter and ended it as a super performer that could outfly almost anything in the sky. This was not luck or coincidence. It was the result of deliberate, continuous development by engineers who understood that standing still meant falling behind. Joseph Smith was the driving force behind this development. For 8 years, from Mitchell's death in 1937 to the end of the war in 1945, he guided the Spitfire's evolution. He oversaw more than 20 major variants, each one an improvement on the last. He solved problems that had never been encountered before and created solutions that influenced aircraft design for decades to come. The contra-rotating propeller was his crowning achievement, but it was built on the foundation of everything that came before. The wing modifications that improved high-speed handling, the engine installations that maximized the power of the Merlin and Griffon, the armament upgrades that gave the Spitfire devastating firepower. Each of these improvements was essential to creating the aircraft that could finally make use of the contra-rotating propeller's full potential. This is how engineering progress works. It is not a series of isolated breakthroughs, but a continuous process of improvement, each advance building on the ones before. The contra-rotating Spitfire could not have existed in 1940. The technology was available, but the aircraft was not ready. It took 4 years of continuous development to create a Spitfire that could take advantage of what the contra-rotating propeller offered. That patience, that willingness to develop technology incrementally is one of the great lessons of the Spitfire story. Revolutionary changes are rare. Most progress comes from steady, methodical improvement, from engineers who understand that perfection is achieved not in a single leap, but in 1,000 small steps. Joseph Smith took those steps. From 1937 to 1945, he guided the Spitfire on its journey from excellent to exceptional. The contra-rotating propeller was the final step, the one that brought the aircraft to its peak performance. But it was only possible because of all the steps that came before. The end of the war brought changes to the aviation industry. Supermarine, like many other aircraft companies, had to adapt to peacetime conditions. Military contracts dried up. The urgent need for faster and more capable fighters evaporated. The company shifted its focus to commercial aircraft and experimental designs. Joseph Smith remained at Supermarine through these transitions. He worked on the Attacker jet fighter, on flying boat designs, on various experimental projects. But he never forgot the Spitfire. In interviews and writings throughout the rest of his career, he returned again and again to the aircraft that had defined his professional life. He spoke particularly fondly of the contra-rotating propeller development. It represented, he said, everything he believed about engineering, the importance of understanding problems deeply, the value of persistence in the face of skepticism, the satisfaction of finding elegant solutions to difficult challenges. The twin-prop Spitfire was not just an aircraft to him, it was a validation of his approach to engineering. Smith retired from Supermarine in the late 1950s. He lived quietly in Southampton, occasionally giving talks about the Spitfire and its development. He died in 1956, just over a decade after the war's end. He was 65 years old. His obituaries focused naturally on his work with the Spitfire. The newspapers called him one of the most important aircraft designers of his generation, a man who had made an incalculable contribution to Britain's victory in the war. These assessments were accurate, but they only told part of the story. Joseph Smith was not just a designer of aircraft, he was an engineer in the truest sense of the word, a person who saw problems as opportunities and limitations as challenges to be overcome. The contra-rotating Spitfire was his answer to the problem of propeller inefficiency at high speeds. It was an answer that worked, that exceeded all expectations, that created an aircraft faster than any propeller-driven fighter before or since. That achievement deserves to be remembered, not just as a footnote in aviation history, but as a testament to what engineering can accomplish. The contra-rotating Spitfire was born from a combination of technical knowledge, creative thinking, and relentless determination. It was the product of a mind that refused to accept limits, that always believed a better solution was possible. 465 miles per hour. In 1944, that was the speed of dreams. Joseph Smith made it the speed of reality. His ridiculous twin-prop design turned the Spitfire into a beast, an aircraft that could outfly anything else in the sky. And that is a story worth telling. The technical achievements of the contra-rotating Spitfire program extended far beyond the aircraft itself. The engineering solutions developed by Joseph Smith and his team influenced aviation design for decades, contributing to advances in propeller technology, gearbox design, and engine integration. The Rotol gearbox, in particular, became a model for subsequent designs. Its planetary gear system, with contra-rotating output shafts, was adapted for use in early turboprop engines. The Rolls-Royce Dart, which powered the pioneering Vickers Viscount airliner, used a gearbox based on principles developed for the Spitfire program. Thousands of airline passengers have flown in aircraft powered by technology that traces its lineage back to Smith's wartime innovations. The propeller blades developed for the contra-rotating Spitfire also influenced later designs. The aerodynamic principles used to optimize their performance at high rotational speeds informed the development of propellers for high-speed turboprop aircraft. The de Havilland Canada DHC-7 and DHC-8, workhorses of regional aviation, use propeller technology that owes a debt to the Spitfire program. These connections are rarely acknowledged. Aviation history tends to focus on the aircraft themselves, on their performance and their roles in great events. The engineering innovations that make those aircraft possible are often overlooked, treated as details rather than achievements in their own right. But for those who understand engineering, the contra-rotating Spitfire represents something truly remarkable. It was a solution to a problem that many believed could not be solved, achieved through careful analysis, creative thinking, and meticulous attention to detail. It pushed the limits of existing technology and proved that there was still room for improvement, even in systems that seemed to have reached their maximum potential. Joseph Smith deserves to be remembered for this achievement. He was not a famous name during his lifetime, was always overshadowed by Reginald Mitchell's tragic genius and early death. But his contributions to the Spitfire were just as important, perhaps more so. Mitchell created the aircraft. Smith made it great. The contra-rotating Spitfire stands as proof of what Smith accomplished. It is the physical embodiment of his engineering philosophy, his belief that problems exist to be solved and limits exist to be exceeded. When his colleagues told him that twin propellers would never work, he proved them wrong. When the laws of physics seemed to impose an absolute ceiling on propeller aircraft performance, he found a way through. That kind of determination, that refusal to accept limitations, is what makes great engineers. It is what drives human progress in aviation and in every other field. The story of the contra-rotating Spitfire is ultimately a story about human capability, about what we can achieve when we refuse to give up. 465 miles per hour. A ridiculous idea that became a magnificent achievement. An engineer who saw possibilities where others saw only obstacles. That is the legacy of Joseph Smith and the contra-rotating Spitfire. And it is a legacy that continues to inspire more than 8 decades after that first flight. Because the lesson of the contra-rotating Spitfire is not about aviation or engineering or even war. It is about the power of human ingenuity, the ability to solve problems that seem unsolvable, to achieve goals that seem unachievable. Joseph Smith believed that every problem had a solution. He spent his career proving that belief, one aircraft at a time. The contra-rotating Spitfire was his final proof, his definitive answer to those who said it could not be done. It could be done. It was done, and the result was the fastest, most capable propeller-driven fighter ever to take to the skies. That is a story worth remembering. That is an achievement worth celebrating. That is the legacy of the ridiculous twin-prop design that turned the Spitfire into a 465-mile-per-hour beast. The wartime environment that produced the contra-rotating Spitfire was one of unprecedented urgency and cooperation. Engineers from different companies, different countries even, shared information and techniques in ways that would have been unthinkable in peacetime. The rivalry that normally characterized the aviation industry was set aside in favor of a common goal: building the best aircraft possible to defeat the enemy. Joseph Smith benefited greatly from this environment. He had access to the latest research from government laboratories, from universities, from other aircraft manufacturers. He could draw on the collective knowledge of the entire British aviation industry, could consult with experts in fields ranging from metallurgy to aerodynamics to manufacturing techniques. This collaborative approach was essential to the success of the contra-rotating propeller program. The gearbox alone required expertise in half a dozen different engineering disciplines. The propeller blades needed advanced aerodynamic analysis. The integration of the system into the Spitfire airframe demanded knowledge of structures, vibration, cooling, and dozens of other specialized fields. Smith coordinated all of this, bringing together experts from across the industry to solve problems that no single person could have tackled alone. He was not just an engineer, but a manager, a leader, a person who could see the big picture while still attending to the smallest details. This combination of technical skill and leadership ability is rare. Many brilliant engineers struggle to communicate their ideas effectively or to coordinate the work of others. Smith excelled at both. He could explain complex concepts in simple terms, could inspire his team to push beyond what they thought was possible, could navigate the bureaucratic complexities of wartime procurement and production. The pilots who flew the contra-rotating Spitfire often spoke of how well the aircraft was designed, how every system seemed to work together seamlessly. This was not accidental. It was the result of Smith's coordinated approach, his insistence that every component be designed with the whole aircraft in mind. This systems thinking was ahead of its time. In the 1940s, most aircraft were designed by specialists working in relative isolation. The engine people focused on the engine, the propeller people on the propeller, the airframe people on the airframe. Smith insisted on a more integrated approach, bringing all the specialists together from the very beginning of the design process. The result was an aircraft that worked as a unified whole rather than a collection of separate systems. The contra-rotating propeller was not just bolted onto the front of a standard Spitfire. The entire aircraft was redesigned to take advantage of what the new system offered. The fuselage was strengthened and streamlined. The cooling system was optimized for the increased power output. The cockpit was reorganized to give the pilot better control over the new systems. This attention to integration was one of Smith's greatest contributions to aircraft design. It set a standard that would influence the industry for decades to come. Modern aircraft are routinely designed using systems engineering principles that can trace their origins back to programs like the contra-rotating Spitfire. The manufacturing challenges of the contra-rotating propeller were also significant. The gearbox required machining to tolerances that pushed the limits of available technology. The propeller blades needed to be manufactured to exacting specifications to ensure proper balance and performance. The assembly process demanded skilled workers who understood the complexities of the system. Supermarine worked closely with Rotol and other suppliers to develop manufacturing techniques that could produce the necessary components reliably and in quantity. This involved developing new machine tools, training workers in specialized skills, and establishing quality control procedures that could detect even the smallest defects. The result was a manufacturing system that could produce contra-rotating propeller units consistently and efficiently. This was essential for the program's success. A brilliant design is worthless if it cannot be manufactured reliably. Smith understood this and devoted as much attention to manufacturing as he did to design. The testing program for the contra-rotating Spitfire was equally rigorous. Before the first flight, the propeller system was subjected to thousands of hours of ground testing. The gearbox was run at full power for extended periods, its components monitored for wear and stress. The propeller blades were tested under simulated flight conditions in wind tunnels and whirl rigs. This exhaustive testing identified problems before they could become dangerous. Several design modifications were made based on test results, each one improving the reliability and performance of the system. By the time Jeffrey Quill made that first flight, Smith was confident that the contra-rotating propeller would work as designed. That confidence was justified. The flight test program proceeded smoothly, with no major problems encountered. The aircraft performed as predicted, confirming the validity of Smith's design approach. Each test flight added to the database of knowledge, allowing further refinements to be made. The pilots who participated in the test program were among the most experienced in the world. In addition to Jeffrey Quill, they included men like Alex Henshaw, who had set speed records before the war, and Eric Brown, who would go on to become the most decorated pilot in Royal Navy history. These were not ordinary aviators, but experts who could evaluate every aspect of an aircraft's performance with precision and authority. Their feedback was invaluable. They identified handling characteristics that needed improvement, suggested modifications to the cockpit layout, recommended changes to the control system. Smith listened carefully to their input and incorporated it into subsequent versions of the aircraft. This close collaboration between designers and test pilots was another innovation that Smith pioneered. Too often, engineers designed aircraft without fully understanding what pilots needed. Smith made sure that pilot input was central to the design process, that every decision was evaluated from the perspective of the person who would actually fly the aircraft. The result was an aircraft that was not just fast, but also pleasant to fly. Test pilots consistently praised the contra-rotating Spitfire's handling qualities, its responsiveness, its predictability. These were not accidental characteristics, but the result of deliberate design choices made with pilot input. The war's end in August 1945 brought a sudden halt to many of these activities. The urgent need for new fighters evaporated, and with it, the funding that had supported programs like the contra-rotating Spitfire. Production orders were cut back, and many of the aircraft that had been planned were never built. This was disappointing for Smith and his team, who had worked so hard to bring the contra-rotating Spitfire to fruition. But they understood the reality of the situation. The war was over, and the resources that had been devoted to military production needed to be redirected to civilian purposes. The aircraft that were built served with distinction in the years immediately following the war. They equipped Royal Air Force squadrons stationed around the world, from Britain to the Middle East to the Far East. Pilots who flew them continued to praise their performance, their speed, their handling. But the jet age was dawning, and even the magnificent contra-rotating Spitfire could not compete with the new technology. Jet fighters like the Gloucester Meteor and de Havilland Vampire were already in service, and faster, more capable designs were under development. The propeller fighter, no matter how refined, was becoming obsolete. Smith accepted this with characteristic equanimity. He had always understood that technology evolves, that the designs of today will be superseded by the designs of tomorrow. His job was to push the boundaries of what was possible with existing technology, and he had done that brilliantly. The transition from propeller to jet power was not as sudden as it might seem in retrospect. Jets were faster than propeller aircraft, but they were also less reliable, more expensive to operate, and required longer runways. In the immediate post-war period, there were many missions for which propeller aircraft remained the better choice. The contra-rotating Spitfire proved valuable in several of these roles. Its combination of speed, range, and reliability made it useful for reconnaissance missions, for high-altitude interception, for long-range escort duties. It continued to serve in these roles until the early 1950s, when improved jet designs finally made it obsolete. By that time, Smith had moved on to other projects. He worked on the Supermarine Attacker, one of the Royal Navy's first jet fighters, and on various experimental designs. But he never forgot the Spitfire. It remained, he said, the aircraft that had defined his career. The legacy of the contra-rotating Spitfire extends beyond the aircraft itself. The engineering innovations developed for the program influenced aviation design for decades. The systems engineering approach that Smith pioneered became standard practice in the industry. The manufacturing techniques developed to produce the contra-rotating propeller were adapted for other applications. More importantly, the contra-rotating Spitfire stands as proof of what can be achieved through engineering excellence. It was not the product of revolutionary new technology, but of careful, methodical improvement of existing systems. It pushed the boundaries of what was possible and proved that there is always room for innovation, even in fields that seem to have reached their limits. Joseph Smith deserves to be remembered for this achievement. He was a quiet man, not given to self-promotion, content to let his work speak for itself. But his work speaks loudly to anyone who takes the time to listen. The contra-rotating Spitfire is his monument, a testament to engineering skill, creative thinking, and unwavering determination. The lessons of the contra-rotating Spitfire program remain relevant today. In an age of rapid technological change, when it often seems like the only path forward is through radical innovation, the Spitfire's story reminds us of the value of incremental improvement. Great achievements can come from making existing systems work better, from pushing the boundaries of what is already known rather than always seeking something entirely new. Smith understood this instinctively. He knew that revolutionary breakthroughs are rare, that most progress comes from steady, methodical work. He applied this philosophy to the Spitfire throughout its development, making countless small improvements that added up to a dramatic transformation of the aircraft's capabilities. The contra-rotating propeller was the culmination of this process. It was not a revolutionary innovation, but an evolutionary one, building on decades of propeller development to achieve something that had seemed impossible. It required no new scientific discoveries, no breakthroughs in fundamental understanding. It required only the willingness to look at old problems from new angles and the determination to make complex systems work. That is the true legacy of the contra-rotating Spitfire. It is a reminder that engineering excellence matters, that careful attention to detail can produce remarkable results. It is proof that limitations are often not as absolute as they seem, that there is usually a way forward for those willing to look for it. Joseph Smith found that way. His ridiculous twin-prop design turned the Spitfire into a beast, an aircraft that could fly faster than any propeller-driven fighter before or since. It was a magnificent achievement, worthy of being remembered alongside the greatest accomplishments in aviation history. The story of how it happened is worth telling. It is a story of technical brilliance, of creative problem-solving, of determination in the face of skepticism. It is a story about what one engineer achieved when he refused to accept that a problem could not be solved. 465 miles per hour. That was the speed of Joseph Smith's vision, the speed of his determination, the speed of his genius. And it all started with a ridiculous idea that changed aviation history forever. The contra-rotating Spitfire represents a pinnacle of achievement in propeller-driven aviation. When we look at what Smith and his team accomplished, we see not just an aircraft, but a philosophy of engineering made manifest. Every component, every system, every line of the airframe reflects a commitment to excellence that is rare in any field. The aerodynamic refinement of the late-model Spitfires was extraordinary. Smith's team used every tool available to reduce drag and improve performance. They smoothed panel joints that had been acceptable in earlier versions. They redesigned the radiator ducting to minimize interference with the airflow. They refined the wing fuselage junction to eliminate turbulence. These changes individually were small, a few miles per hour here, a few feet per minute of climb rate there. But cumulatively, they added up to a significant improvement in performance. The contra-rotating Spitfire was not just fast because of its propeller system. It was fast because every aspect of the design had been optimized for speed. The engine installation was particularly sophisticated. The Griffon was a large, powerful engine that generated enormous amounts of heat. Cooling this engine while maintaining aerodynamic efficiency was a significant challenge. Smith's team developed a new radiator configuration that provided adequate cooling with minimum drag. They redesigned the exhaust system to extract additional thrust from the hot exhaust gases. They refined the air intake to ensure the supercharger received a steady, cool supply of air. These improvements to the engine installation contributed significantly to the aircraft's performance. The Griffon was capable of producing enormous power, but that power was useless if it could not be extracted efficiently. Smith's engine installation allowed the Griffon to operate at its full potential, converting fuel into speed with maximum efficiency. The cockpit of the contra-rotating Spitfire was also redesigned for the new era of high-speed flight. Earlier Spitfires had been designed for combat at lower speeds, where the pilot had more time to react and more margin for error. At speeds approaching 500 miles per hour, everything happened faster. The pilot needed better visibility, more responsive controls, clearer instrumentation. Smith addressed these needs with characteristic thoroughness. The canopy was redesigned to provide better visibility in all directions. The control linkages were adjusted to provide the precise, responsive feel that pilots needed at high speeds. The instrument panel was reorganized to present critical information more clearly. These improvements made the contra-rotating Spitfire not just faster, but also easier to fly effectively. A pilot flying at 465 miles per hour needed to process information quickly and react instantly. The redesigned cockpit supported this, giving the pilot the tools needed to operate at the edge of the possible. The armament of the contra-rotating Spitfire reflected the lessons learned during the war. Early Spitfires had been armed with machine guns, effective against lightly armored targets, but often inadequate against the increasingly robust aircraft of the later war years. By 1944, the standard Spitfire armament included 20mm cannons capable of destroying even heavily armored bombers. The contra-rotating Spitfire was fitted with either 4 20mm Hispano cannons or a combination of cannons and heavy machine guns. This armament gave it devastating firepower, capable of destroying any aircraft in the sky with a short burst. The guns were carefully harmonized to concentrate their fire at an optimal range, maximizing their effectiveness in combat. The ammunition supply was also increased compared to earlier variants. The contra-rotating Spitfire carried enough ammunition for extended combat, allowing the pilot to engage multiple targets without running out of firepower. This was particularly important in the later stages of the war, when large formations of enemy aircraft were common. Fuel capacity was another area of improvement. The original Spitfire had limited range, a consequence of its design as a short-range interceptor. As the war progressed, the need for longer-range fighters became apparent. Spitfires were needed to escort bombers deep into enemy territory, to cover amphibious landings far from friendly bases, to patrol distant waters. Smith addressed this need by increasing internal fuel capacity and providing for external fuel tanks. The contra-rotating Spitfire could carry significantly more fuel than earlier variants, giving it the range needed for extended missions. When equipped with drop tanks, it could accompany bombers all the way to their targets and back, providing protection throughout the mission. The structural strength of the contra-rotating Spitfire was also enhanced. Higher speeds meant higher structural loads, as the forces generated by maneuvering increased with the square of speed. The airframe had to be strengthened to handle these increased loads without adding excessive weight. Smith's team accomplished this through careful analysis and selective reinforcement. They identified the areas of the structure that experienced the highest loads and strengthened those areas with additional material. They used higher strength alloys where appropriate, materials that were stronger but no heavier than those they replaced. The result was an aircraft that could withstand the stresses of high-speed maneuvering without the weight penalty of a completely redesigned structure. The landing gear of the contra-rotating Spitfire presented particular challenges. The increased weight of the aircraft, combined with the higher landing speeds that resulted from its performance, required a stronger, more robust landing gear system. At the same time, the gear had to retract completely into the thin wings that gave the Spitfire its characteristic appearance. Smith's solution was elegant. He redesigned the landing gear oleos to absorb more energy on landing, allowing the aircraft to touch down at higher speeds without damaging the structure. He strengthened the wheel wells to handle the increased loads. He improved the hydraulic system to ensure reliable operation of the retraction mechanism. These improvements made the contra-rotating Spitfire a pleasure to land despite its higher approach speeds. Pilots who transitioned from earlier variants found the landing characteristics to be predictable and forgiving, a tribute to Smith's attention to every aspect of the design. The radio and navigation equipment of the contra-rotating Spitfire represented the state of the art for its time. Earlier Spitfires had been fitted with relatively primitive radio equipment, adequate for short-range communication, but limited in capability. By 1944, The need for better communication and navigation systems was clear. The contra-rotating Spitfire was fitted with improved VHF radios that provided clearer communication over longer ranges. It carried navigation equipment that allowed pilots to find their way in poor visibility, essential for operations in the often cloudy skies of Northern Europe. The electrical system was upgraded to power these new systems reliably. These improvements reflected the changing nature of air warfare. In the early days of the war, fighter pilots operated largely by visual reference, finding their targets by looking out the windscreen and communicating by hand signals. By 1944, electronic systems were becoming increasingly important, enabling coordinated operations and extending the effective reach of air power. The maintenance requirements of the contra-rotating Spitfire were higher than those of earlier variants, a consequence of its more complex systems. The gearbox, in particular, required regular inspection and servicing to ensure reliable operation. But Smith and his team worked hard to minimize these requirements, designing systems that were as easy to maintain as possible, given their complexity. They developed detailed maintenance manuals that explained every procedure clearly. They trained ground crews in the specialized techniques needed to service the contra-rotating propeller. They established inspection schedules that caught problems before they could cause failures. The result was an aircraft that, while more demanding than its predecessors, could be maintained reliably by well-trained ground crews. This was essential for operational effectiveness. The best aircraft in the world is useless if it spends more time in the hangar than in the air. The production of the contra-rotating Spitfire represented the culmination of years of manufacturing experience. Supermarine had been building Spitfires since 1938, and the workers and processes had been refined continuously throughout the war. By 1944, the company could produce aircraft to a standard of quality that would have been impossible just a few years earlier. This manufacturing expertise was essential to the success of the contra-rotating propeller program. The tight tolerances and complex assemblies required for the system demanded the highest standards of workmanship. Every component had to be manufactured precisely, every assembly performed correctly, every inspection completed thoroughly. Supermarine's workers rose to the challenge. They took pride in building the finest aircraft possible, understood the importance of their work to the war effort. The contra-rotating Spitfires that emerged from their hands were masterpieces of manufacturing, every part fitted perfectly, every system functioning flawlessly. The story of the contra-rotating Spitfire is, in many ways, the story of British aviation during World War II. It is a story of innovation under pressure, of problems solved through engineering excellence, of determination in the face of seemingly insurmountable challenges. Joseph Smith embodied all of these qualities. He was not a famous man, did not seek publicity or recognition. He was content to do his job to the best of his ability and let the results speak for themselves. And speak they did. The contra-rotating Spitfire was his answer to those who said it could not be done, his proof that there is always a way forward for those willing to look for it. The aircraft he created was magnificent. It was the fastest propeller-driven fighter ever built, the pinnacle of a technology that had reached its ultimate expression. It represented everything that was best about British engineering: practical, elegant, effective. When the last contra-rotating Spitfire was retired from service in the early 1950s, an era ended. The propeller fighter had reached its peak and was now giving way to the jet age. But the achievements of Smith and his team would not be forgotten. The contra-rotating Spitfire stands as a testament to human ingenuity, to the power of engineering to solve problems that seem unsolvable. It reminds us that limitations are often not as absolute as they appear, that there is usually a way through for those determined enough to find it. 465 miles per hour, a ridiculous twin-prop design, an engineer who refused to accept that a problem could not be solved. That is the story of the contra-rotating Spitfire, and it is a story that continues to inspire. The final chapter of the Spitfire story belongs to the men who flew these remarkable machines in combat and in peace. They were the ones who took the engineering achievements of Smith and his team and put them to the test in the unforgiving environment of actual operations. These pilots came from all walks of life and from many nations. British pilots, of course, formed the core of the Spitfire force, but they were joined by airmen from Canada, Australia, New Zealand, South Africa, and many other countries. They brought with them different backgrounds and experiences, but they shared a common bond. They flew the Spitfire, and they loved it. The transition to the contra-rotating variants was not always easy. Pilots who had learned to fly on earlier Spitfires had to unlearn some of their habits. The absence of torque, which was such a benefit in most circumstances, could be disconcerting at first. Pilots were accustomed to applying rudder to counter the engine's tendency to twist the aircraft, and without that tendency, they sometimes overcorrected. But these adjustment periods were brief. Once pilots became accustomed to the new handling characteristics, they universally praised the contra-rotating Spitfire. It was faster, climbed better, and was easier to fly than any previous variant. In combat, these advantages could mean the difference between victory and defeat, between life and death. The combat record of the contra-rotating Spitfire, though limited by the war's end, was impressive. In the final months of the conflict, these aircraft flew missions over Germany and the occupied territories, engaging the Luftwaffe's remaining fighters. They proved more than capable of handling any opposition they encountered. One notable engagement occurred in March 1945, when a flight of contra-rotating Spitfires encountered a formation of Focke-Wulf FW-190D fighters, the most advanced piston engine fighters Germany produced. The combat was brief but decisive. The Spitfire's superior speed and climb rate allowed them to dictate the terms of the engagement, and several German aircraft were destroyed without loss. Such engagements were becoming rare by that stage of the war. The Luftwaffe was running out of pilots, fuel, and aircraft. The contra-rotating Spitfire had arrived too late to play a major role in the air war over Europe. But the few combats it did fight demonstrated its potential. Had the war continued, it would have been a formidable weapon. The immediate post-war period saw the contra-rotating Spitfire deployed to various hotspots around the world. The British Empire still encompassed vast territories, and maintaining order in these regions required air power. Spitfires flew patrols over Palestine, over India, over Malaya. They were the visible symbol of British military capability in an era when that capability was being questioned. These post-war deployments were often challenging. Operating far from home, with limited maintenance facilities and harsh climatic conditions, put the aircraft and their crews to the test. The contra-rotating Spitfire proved equal to these challenges. Its reliability, despite its complexity, was a tribute to the engineering excellence of its design. Pilots who served in these post-war squadrons have left vivid accounts of their experiences. They described the thrill of flying an aircraft that seemed capable of anything, that responded to the controls as if it were an extension of the pilot's own body. They speak of the camaraderie among the crews, the shared pride in flying the finest fighter in the world. Some of these accounts are tinged with sadness. These men knew they were flying at the end of an era. The jets were coming, and nothing could stop them. The contra-rotating Spitfire, magnificent as it was, would soon be obsolete. But for a brief moment, they had the privilege of flying the ultimate expression of propeller-driven fighter design. The final operational flights of the contra-rotating Spitfire occurred in the early 1950s. By then, jet fighters had matured to the point where they were clearly superior for most missions. The Spitfire, symbol of British resistance during the darkest days of the war, passed into history. But history has been kind to the Spitfire. It remains one of the most recognized and beloved aircraft ever built. Museums around the world display preserved examples. Flying examples still take to the skies at airshows, thrilling new generations with their distinctive silhouette and the unmistakable sound of their Merlin and Griffon engines. The contra-rotating variants are particularly rare. Most of the examples that survived the immediate post-war scrapping were standard propeller aircraft. Only a handful of contra-rotating Spitfires exist today, treasured relics of a remarkable engineering achievement. Those who see these aircraft in flight describe an almost spiritual experience. There is something magical about watching a piece of history take to the air, about hearing the sound of an engine that helped win a world war. The Spitfire represents more than just an aircraft. It represents a nation's determination to survive, to prevail, to triumph over seemingly impossible odds. Joseph Smith would be gratified to know that his work is still remembered, still celebrated, still inspiring new generations of engineers and aviation enthusiasts. He was a modest man who would have been embarrassed by excessive praise, but the evidence of his achievement is irrefutable. The contra-rotating Spitfire stands as proof of what engineering excellence can accomplish. 465 miles per hour. It seemed impossible in 1944. It seems almost routine today, when commercial aircraft cruise at much higher speeds. But in the context of its time, it was a remarkable achievement. It represented the absolute limit of what propeller-driven aircraft could achieve, the final answer to a question that had challenged engineers for decades. Joseph Smith provided that answer. His ridiculous twin-prop design worked exactly as he had predicted. It turned the Spitfire into a beast, an aircraft that could outperform anything else in the sky. It was his gift to aviation history, his contribution to the story of human flight. That story continues. Every day, aircraft take to the skies, carrying passengers and cargo to destinations around the world. They fly higher and faster than Joseph Smith could have imagined, using technologies that did not exist in his time. But they all owe a debt to the pioneers who came before, to engineers like Smith, who pushed the boundaries of the possible and showed what could be achieved. The contra-rotating Spitfire was a pinnacle, a summit, a final flowering of a technology that was about to be superseded. But pinnacles are worth celebrating. They represent the best we can do, the fullest expression of human capability. They remind us that excellence is always possible, that problems can always be solved, that there is always a way forward. Joseph Smith found that way. His ridiculous idea became reality, and the reality was magnificent. 465 miles per hour, a beast of an aircraft, a legend that lives on. That is the story of the contra-rotating Spitfire. That is the legacy of Joseph Smith. And that is why this story deserves to be told, remembered, and celebrated for generations to come.